Hello everyone. The topic for this lecture is resistive power. In other words, we're going to learn how much power do resistors consume. How do we calculate this power, and essentially what happens to this power? So let's begin our discussions by starting from the stuff that we already know regarding power. We do know that the power that a passive device, a load in other words, consumes is equal to the voltage drop across the load divided by the current that flows through the load, provided that you have used passive sign convention for your device. Now, in general, I and V are not necessarily related, but for a resistor, they are. We have already learned, for example, that V is equal to IR in the passive sign convention for a resistor, and therefore I can either replace V or I in this equation to find two additional ways of calculating the power. For example, if I go ahead and replace the voltage drop of the resistor, I can write down this as equal to IR for the voltage times I, or a very famous equation that says that the power consumed for a resistor is equal to I square R. Alternatively, I can go ahead and replace my current in this equation, and therefore I will have that P is equal to V times V divided by R, where now this is Ohm's law for the current, and therefore I can write down that this is equal to V square, voltage square, divided by R. Now, both of these equations are equally good. In other words, you can equally well find the power consumed by a resistor by either squaring the current and multiplying by the resistance, or squaring the voltage and multiplying and dividing rather by the resistance. Notice that this power will always be positive in either case, of course, and that is always correct. A resistor is a passive device, is a load that essentially converts electrical power to heat. So the power consumed by a resistor must always be positive, except for the case when the resistance itself is negative. Now you might say, can we really make negative resistors? Well, you can't make negative resistors by just putting a few conductors together, but you can make an effective negative resistor by using electronic circuits that we will discuss more towards the end of this class, and of course in more advanced courses. For right now, I think it's good to remember that essentially the power consumed is I square R or V square by R for resistance, and it's always positive for normal, typical resistances. Also, I want to clarify, even though this may be obvious so far, that this equation here, meaning power is equal to voltage times current, is a general equation and applies for any device that you might have. On the other hand, these last two equations are specific to resistances, so specific to R, because we've used Ohm's law to derive both of them. So keep in mind that you can only use them for resistances, while the V times I is something you can use anytime. Now, let me use a little bit of a practical example here so we can think about the impact of the power consumed on a resistance. And the practical example I'm using here essentially is asking the question of what happens when you connect an ideal voltage source to your load. In real life, your voltage source or your power supply in general will not be sitting literally right next to your load. In many scenarios, there is some physical distance between where you're generating the power and where you're consuming this power. So it's always or almost always necessary to find a mechanism to transfer the power from point A, where you generate it, to point B, where you consume it. Even though there are different ways you can make this connection, by far the most common way is to basically connect a wire from your source to the load. Now, this wire will never be ideal. It's made out of a real conductor. A lot of times this is copper, and that means it will have some resistance. Yes, the resistance will be small, but it will not be zero. And so whenever you do that connection, it's quite common to represent that wire with some model. The easiest model that we can think about, and certainly an accurate one for DC circuits, is to simply replace the wire with its effective DC resistance, R wire. When we talk about AC circuits, this model may become more complicated, but for DC, a piece of wire is really just an effective resistance. Now, that effective resistance will actually do two things for you. In general, both of them are undesired. The first thing is that it will influence the resulting current. So if you basically calculate the resulting current, it will now be smaller than it would have been if you had directly connected your voltage source to your load, because now that additional resistance of the wire impedes this current flow. But even worse than that, this resistance will actually consume power. So the wire, in other words, will now consume some power, which will be equal to the amount of current that will flow over the resistance of the wire. So I square R will be a positive power that essentially will help transfer some of the electrical energy you were hoping to give to the load to now heat. Of course, this is highly undesirable, and a lot of times we will do this, we will prevent from having this effect having a real influence in our circuit by making this R wire as small as possible. Now, how can you do that? One way you can do this is by literally shortening the distance between your source and your load. Sometimes that's possible, but other times it's not. For example, imagine that you're generating power from a substation and then you have to now take this power back home. You can't move the substation, you can't move your house, and that means that that distance is fixed. So what's the only other alternative? Well, the only other alternative is to reduce this wire by essentially choosing a better conductor. And you honestly, a lot of times you can't choose the material of the conductor, so really the only thing you can do is you can use a wire with a much wider cross-section A in order to essentially reduce the amount of resistance. As you can imagine, this wire with a large cross-section will have a much lower resistance than a wire with this green cross-section that is essentially much, much smaller. So there are guidelines for many applications, and I want to give you just one of them. It's called the American Wire Gauge, or AWG, where for many common applications and for many common conductors, people have calculated the amount of resistance that you have, and they give you an idea of what's the maximum amount of current you can transfer through this wire in reasonable scenarios, in everyday situations. You can see, for example, that we have names for these wires that have different gauges. Each one of these gauges represents a different diameter of the wire, and that means that you have a different resistance per 1,000 feet for this wire. So that essentially translates to a maximum amount of current that you can transfer. So a lot of times we will see how much current we need, and we will give a safety factor to ourselves, and that means we will select the right gauge. There are many different factors that will influence your selection. For example, it will be influenced by the temperature of the environment that you plan to do this. But in this case, I don't want to go through those details. All I want to alert you is that there is a guideline that links the maximum amount of current that you need to transfer to the specific diameter of the conductor, given that you have chosen the material. So thank you for watching this lecture. I hope you have a better understanding for resistive power and some of its effects, and we will see you next time.